time, it's a waveform or is a time function? That's a signal. Most of the time in this course, we're going to deal with unilateral or one-sided signal. That means that we assume that signal takes value 0 before time 0. Everything's dead, it's silent before time 0. So only the signal start to become non-zero after time 0. Right? Signal, right, it's 0 for all t less than 0. Then that's called a unilateral one-sided signal. A typical such signal is called a unit step signal. This is something we're going to use all the time. Unit step signal is just like a 0 everywhere here, then it jump to 1 after time 0. Okay. You probably have seen this before. So this is probably the simplest signal we're going to use. That we're going to use all the time. Simplest unilateral signal. Unit step, we are going to use a unit impulse signal as well. But this signal is a bit more like a mathematical abstraction because it's a kind of a strange thing. It's not quite a function. It's called a singular function. So this unit impulse signal is defined in such a way. Okay. First of all, it's a 0 everywhere, except at time 0. But at time 0, something strange happens. If you integrate from minus infinity to t, well, if this t is less than 0, you see what happens. Because this signal is, well, maybe we'll just look at it here, okay? Forget about this step. We are just have a signal 0 everywhere here, 0 everywhere there. It just have something strange happen here at time 0. So if you integrate the function from minus infinity to t, and if this t is somewhere here, it's less than 0, of course, from minus infinity to t, everywhere is 0, integrate is still 0. Okay? But if the t is somewhere here, you know that this is something strange happened at this origin, then the integral from minus infinity to somewhere here becomes non-zero. It turns out actually the integral is equal to 1 if you integrate from here. So that means, okay, this integral, the integral of the unit impulse function from minus infinity to t is equal to this guy. Right? So you know that the function value is 0 here, 0 over there. So if you integrate from minus infinity to somewhere here, you're doing nothing most of the time, except when you go from here to there, right? Basically from minus infinity all the way integrate, up to this point you're not doing anything. And after this time zero, you go further, you're not doing anything. The only strange thing happening is that is from here to there. So this integration actually is equal to the integration from t minus to t plus. No. From 0 minus to 0 plus. Right? That's something. What is that 0 minus 0 plus? 0 minus is just a bit before 0. 0 plus is just a bit after. You see that when you integrate, you can simply take that as small integration. You integrate in a small integration. The unit step, the unit impulse, after integration you get a step, unit step. So the integral of this is equal, integral of theta is equal to sigma, then the derivative of sigma gives you theta. This is according to the calculus. The differentiation is the opposite. It's the inverse operation of integration. So now you see that this definition of unity impulse signal is kind of abstract, right? It defined not as a usual function. We define that as the value at each time. It's defined in terms of this differentiation or integration. But we can actually use we can also use some kind of approximate argument. Suppose that we have a signal like this. So this can be considered as an approximate step. Instead of having a jump at the time 0, now I have like a slope, a ramp, going like a very rapidly to 1. It takes a time, an epsilon time interval to go from 0 to 1. So certainly this is approximation of this. Now let's take the derivative of this. The derivative of this, see, we go 0 here, and 0 over there, the derivative. But this derivative is 1 over epsilon, very high. So when you shrink this epsilon, make this epsilon very, very small, then this interval becomes very, very small, but the height becomes huge. The area below this is a constant, is 1. So this is an approximation of theta, the impulse function. Okay. When epsilon becomes smaller, you get a better approximation. So that's a whole idea here. Yeah, you can always think this beta function in this way. So it's a very high impulse, a very narrow impulse, so that you have a fixed area. Those two signals are the ones we're going to use all the time. And then in other courses, you also use these two signals. So you can imagine also other unilateral signals. So you see that this sigma t is not only itself is not only, it's not only can be defined by, like independently as a signal, but it can also be used to describe or to write a unilateral signal with other features. For example, we say sine function, sinusoidal signal. That's something you very often you see. But sinusoidal signal, right, goes from minus infinity to infinity. It's just a periodic going up and down. You multiply your data, what do you get? You get a unilateral sinusoidal signal. Basically, it's a sinusoidal signal starting at time 0. So before time 0, it's just flat, 0. Okay? So this sigma t gives you a convenient way to describe a unilateral sinusoidal signal. Also, this signal, this e to the lambda t, e to lambda t is exponential signal. This kind of signal is often kind of some kind of a common signal. Exponential signal, probably we should look at that more closely. Suppose we wish to look at a unilateral exponential signal. So in that case, we know that this side is always 0. So we only need to worry about the positive time axis. Positive time axis, okay. When this t is 0, when this t is 0, e to the power of 0 is e to the power of 0 is 1. It starts from here. 1. So when time goes by, how is this going to go down or go up? Huh? Yeah, it depends on lambda, right? So if lambda is less than 0, it goes down, right? So it goes down exponentially, we say. Exponentially goes down. So in that case, this lambda is less than. When t goes to infinity, converge to 0, right? It will never be 0 exactly. It converges to 0. And monotonically converge to 0. Right? That's